All right, we move to the topic of climate. So the last topic being carbon cycle, and that should have helped us. Well, I guess there are a couple topics kind of together, but the last topic directly related to this being the carbon cycle. And from there, hopefully we understand the difference or the imbalance that's begun to happen with carbon on the planet. And in order to really draw that connection between carbon and temperature, we have to understand some of the specifics of climate. And I think without understanding climate, it's pretty difficult to understand climate change, which is where we're going. So here are some of the goals, or here is the goal and some of the objectives for today. Again, reminding you that you can use these to test your knowledge after the lecture, before a test, what have you. Okay, so weather versus climate. A big challenge that sometimes seems to happen in the climate change discussions is a lack of understanding about the difference between weather patterns and climate. So weather is the day-to-day precipitation and temperature, that variability that you'll see when, if I look outside right now, it happens to be sunny and hot, really hot today. However, tomorrow it might be rainy and a bit cooler, right? That would be a weather pattern. Whereas climate are the long-term weather patterns that are sustained over a period of time. So here we are in South Carolina, we're in a temperate climate. And we actually have a pretty good rainfall here in a typical year. So a little bit more on a higher precipitation scale, and in a climate where we have 4 full seasons, but we also have a little bit warmer. We don't get as cold, so we're closer to the equator, and that keeps us from getting as cold as areas up north, right? So those are our climate patterns, where we have general expectation of temperature variability, what the seasons might look like, and rainfall patterns that we would expect to experience in any given year. Okay, so there's just a little bit of definitions for you. So what influences climate? Backing up a second, what influences weather is going to be, there's going to be a lot of variation, right? You're going to have your winds that are moving warm air at any given time or moving cold air. And those are going to, those are very, at times almost random, and those are going to impact those weather patterns at any given time. But climate, so what influences climate, which again, those long-term sustained patterns, has to do with several factors that we're going to cover in the next few slides. The first is this unequal heating of the earth. So if you look, the earth is on an axis. We're actually tilted. It is not directly up and down. And so the earth is sitting on an axis like this out in space. And we get more direct solar radiation happening towards this middle line. So if you look at the equator here, that's getting more direct solar radiation throughout the year. And these poles are getting radiation at more of an angle. We call that insolation, so that's just a measure of the solar radiation falling on a surface. Another factor that's going to influence climate is albedo. So albedo is the reflectance of a surface of the Earth. If something has high albedo, it actually reflects a large amounts of solar energy. And what happens is so the clouds is a good example because clouds can have very high albedo, is that solar energy hits the clouds and it does not change wavelength. So it just radiates back out into space in a similar pattern to how it came in. Sea ice is another very high albedo object. So it hits here and it just radiates, it bounces off the earth and radiates back out into space. Areas of lower albedo, the lowest albedo is asphalt. And when solar radiation hits these types of areas, it's actually going to be changing its wavelength and basically staying closer. Less of it's going to be reflected back out into space, and more is going to stay closer to that surface of the earth. And we've all sort of felt this when you're on a black asphalt surface, you can have these little microclimates where it might be warm here and a little bit cooler over here. Now, some of that would have to do with shade, but it could also, if you're in a grassy area, that would have to do with some of that albedo effect. Okay, so here's 2 really good thought questions. And one of these was quite a bit developed in the book chapter. So how does albedo contribute to warming and cooling feedback loops? Now would be a good time to kind of pause the video and think about those for a minute, maybe write out a little answer to it. But as was discussed in the text, what happens with albedo, and so sea ice is a really good example. If we have a warming climate, we start to melt sea ice. When we melt that sea ice, we're actually decreasing the Earth's average albedo. And as that occurs, we're going to end up with a warmer overall planet, which is then going to melt more sea ice, which is then going to decrease the albedo. And so we get what we call a positive feedback loop of a warming planet. The same thing can happen in the opposite direction. And the text referred to that as a snowball Earth, where you would get a cooling planet, you would get more sea ice that would increase the average albedo, and the planet gets cooler. And they believe that something like that, that feedback effect has happened historically in ice ages. Other factors that influence climate, this is the big one, the greenhouse effect. So named the greenhouse effect because it's similar to the concept of a greenhouse. And I don't have a greenhouse here, I have a picture of a car, but the same thing is happening with your car's windows. So we all know here in South Carolina, we like to avoid parking in really bright sunny spots. And it's because when you come back in your car, you can barely sit down because there's so much heat generated in that car. What happens is the solar radiation comes into the car and it passes directly through the windshield, but then it's actually re-radiated back out and it changes frequency. And so wavelength, sorry, it changes its wavelength. And in doing so, it actually can't pass, the energy can no longer go directly back out through the windshield. So you create this warming space in here, which is that greenhouse effect. And this is what is happening on the surface of the planet, or in the atmosphere of the planet. So we have this invisible blanket that is our greenhouse that is composed of atmospheric gases. So without these atmospheric gases, we would live in a very cold planet. And what these atmospheric gases do is some of that, some of the sun energy that comes in is actually going to go ahead and change its wavelength. It's going to, and it's going to be radiated back down to Earth, right? So we actually have this infrared radiation that's going to go ahead and kind of stay in this layer of the atmosphere of the Earth, overall causing a warmer Earth atmosphere, right? And so these greenhouse gases that we cannot see are actually absorbing and re-emitting this radiation that is heating up our planet. And it's happening at a chemical level, so we can't see it, but we know it's happening, in part because we're able to chart the effect. We're able to look at the reaction on a small scale, and then we're able to chart the effect over large scale, which I'll be showing you in a minute. Okay, so first, what are these main greenhouse gases? This one here, you've been hearing a lot about already. Back in 2010, it was at 390 parts per million in the atmosphere. As I've mentioned on several occasions, we're above that now. And just a little reminder, this back 10 years ago was already, or approximately, right, was already well above the 350 parts per million barrier for the for climate change and the planetary boundaries. Other things that are in the atmosphere that have a greenhouse effect: water vapor. Water vapor, however, we don't worry about because it can only last 8 to 9 days in the atmosphere. So it has a net zero impact on global warming, except for the fact that with a raising with a raising atmospheric temperature, the atmosphere is actually able to hold more water vapor at any given time. And so therefore it has a slightly larger effect than it would have at a lower temperature. Okay, other major ones: methane. This is CH4, and this is primarily from decomposing things. Nitrous oxide, this already came up a little bit with the nitrogen cycle, but the nitrous oxide can be released into the atmosphere. And then chlorofluorocarbons. So all of these things have a greenhouse effect. These are major greenhouse gases. There are some more minor ones, but these are the major ones. And what I want you to notice here is this global warming potential. So note, these numbers, the higher this number is, that's the more energy each molecule would tend to absorb and re-radiate. So if you have a higher number, it means you have a bigger impact factor on the heating of the climate. So we pay a lot of attention to carbon dioxide, which is the one that we emit the most of, and that's why we pay the most attention to it. However, it has actually a much lower global warming potential than some other things that we're putting in the atmosphere. Methane is increasingly becoming more and more of a concern because we're, with our switch to natural gas, on the one hand, natural gas is methane. It burns more cleanly, but we're also tending to allow more to escape into the atmosphere without being burned cleanly. And so all of this goes to say there's these gases we're putting in the atmosphere. These ones we put less of into the atmosphere, but each molecule we put in there has a bigger impact. And carbon dioxide, as you know from our carbon cycle, we are dumping tons and tons, billions of tons of it into the atmosphere every year. Okay, this is just reminding you about seasons. The Earth goes around the sun, and when the northern hemisphere is facing more directly towards the sun, which is actually this point, that is when we have our June solstice, which is June 21st, and often we say marks the beginning of summer, but it's actually the longest day of the year. And then the winter solstice being December 21st, and that's when the southern hemisphere is getting the most direct solar radiation. And then we have a March and a September equinox. Another factor influencing climate is is Milankovitch cycles. Milankovitch cycles tends to be a confusing topic to students, and I think it's because they don't pay attention to these numbers right here. So 19 to 24,000 years, 41,000 years, 100 to 400,000 years. So what these are changes in the Earth patterns around the sun. It's the changes in the shape of the Earth orbit, the tilt of the Earth, so if it's more upright or if it's more tilted, and then the precession, which is how much that Earth is wobbling as it moves around the sun. So if you think of like a top, when it's starting to sort of, tops can spin perfectly on their little, I don't know, point. And then when it starts to sort of lose speed, it starts to wobble more. So when it's more wobbly, it's got a bigger precession. And then when it's more upright, it has less of that. So the Earth is going to be changing its orbit over these different cycles. So between 100 and 400,000 years, we get more ovular orbit, or a more sort of circular orbit, although note it's always ovular. And then we have over here a more, on 19 to 24,000 years, we have this more wobbly to less wobbly orbit. And then that tilt is going to change on this 41,000 year cycle, right? So between 21 and 24 degrees. Okay, and then at any given time, if you just think about these working on different time scales, you're going to have a different combination of them in effect. However, I always get students talking about, looking at changes in temperature since the 1800s, and they'll throw out maybe it's Milankovitch cycles. That doesn't make sense if you look at the time scales that these are operating on, right? They were on very long time scales. This is not 100 years. So the observed changes we're seeing in current climate, again, we're not looking at, we would not expect Milankovitch cycles to influence climate on a short time scale. On 1,000, 2,000, 10,000, 20,000 year time scale, certainly. And so later we're going to look at some graphs and just pay attention to what that time is, the time scale, and some of the changes that you're seeing. Thermohaline circulation, there's a great video on this that I think makes it a lot easier to understand than this, so make sure to watch that video. But overall, this is the idea that the movement of water in our oceans greatly influences the climate on the surface of the planet, or on land surfaces. So these red ones are showing you warmer waters. And these warmer waters circulate the globe, and they actually bring warmer water up from like the equator and it flows up. And actually, that warm water is what makes this very northern region of Europe nice and inhabitable. Without this warm water flow, if you look at where it is, it would be a lot colder up there. And then when it gets up to the poles, what happens is that you've evaporated off a lot more water. So you have saltier, denser water that then sinks to the bottom at the poles. And water is magnetic. So we've all seen water, it's a slightly magnetic molecule, and you've all seen water droplets form and how they kind of stick together and will slide down a surface together. And so what happens with that magnetic water is that it will pull down the top layer. So you have this conveyor belt, if you think of like, we've all seen a conveyor belt, that's pulling water all over the surface of the planet. When I want you to remember this, because when we get to climate change, this thermohaline circulation is going to become important because of melting polar ice caps that are diluting this water here and keeping it from being as salty as it has been. That can potentially cause dramatic impacts on this thermohaline circulation patterns. Okay, so just here's looking at what we expect for the climate in the globe, right? So annual mean precipitation, I mentioned we're around here, so we are in a quite fairly high wet area of the globe. If you look over here, we talked about some of the water problems faced in the southwestern United States. They're an extremely low precipitation pattern area of the globe. And so this is just generally what we expect in terms of climate patterns and long-term precipitation. We've already seen these biomes, and we know that our biomes are influenced by climate. And then there's the air movement as well. So now air movement causes these more sporadic weather patterns. So the Earth moving on its axis generates winds. And also we get a rising of hot air and a cooling of cold air. And these multiple combinations of factors are going to cause particular weather patterns at any given time. So how do we track climates over time? We have these things that we can study, which we call proxies. And I do want you to remember that term, proxies. And what a proxy is just an indicator where you're able to study one thing as an indicator for something else. So because you can't study the exact thing, you're studying something, a similarly related phenomenon to understand that thing. So one of the best proxies that we have are these ice cores. And the ice cores are, they actually create these layering effect of snow falling at different times and then freezing, forming blocks of ice, right? And so what happens with these ice cores is we have gas trapped in there, and we're able to study the gases in order to understand atmospheric composition and also temperature patterns. So in warmer temperatures, you're going to have more plentiful molecules of a certain types of isotopes in the snow than you're going to have in other cooler temperatures. So we're able to look at those throughout, and then the depth is going to have to do with how old that ice is. So you can cast back in time by looking at the depth of those ice layers, and then you can look at the atmospheric composition of the time to understand atmospheric composition and temperature changes because of those varying isotopes. So this is just showing you the oxygen isotopes that are particularly used to track this, right? And so in general, so water is going to become lighter as it travels towards the poles, and that heavier O18, so that's the heavier oxygen isotope, is going to drop out of the atmosphere before it reaches the ice sheet, which is going to, it's allowing us to track basically how warm, so how far they travel has to do with how warm that atmospheric temperature is. And so that's allowing us, when we look at the ratio of these oxygen, the O18 to O16 isotopes, it allows us to understand variations in temperature. So it'll make it further depending on that atmospheric temperature. So if you look at these, looking at the oxygen isotope in the atmosphere, right? And it gives us an idea of what that temperature change is in degrees Celsius, right? And so, so looking here, casting back, right? So we've got from 0 to 5.5 million years ago. And what we're seeing here is this changes, the changes in the ratio of oxygen isotopes. That's giving us an idea so we can understand climate change over these really long time scales. So when we're looking at these, again, millions of years time scales, one of the things that we're seeing are these Milankovitch cycles, right? We're expecting the Milankovitch cycles to operate on this long time scale so that we can understand these warming and cooling periods. Okay, so when you look at this, the temperature variation, so changes in temperature variation, you can see that there's this perfect correlation between temperature variation, right? Again, these lower numbers being cooler periods, and then these higher numbers, and here you're seeing it at 0 because this again is variation from the present, right? So if you cast back 50,000 years ago, it was a colder period. If you go back as far as 125,000 years ago, we had what looks like the warmest spike we'd had in a while. And then you can go back and trace the climate that way. You see that carbon dioxide concentrations in the atmosphere have almost always perfectly coincided with those temperature variations. Dust concentration in the atmosphere is going to have an opposite effect. So when you have higher dust concentrations in the atmosphere, you're actually having a higher albedo in the atmosphere, and these dust concentrations are going to have a cooling effect on the planet. So these periods when dust is high, we actually have a colder planet, and the periods when the dust is low, we have a warmer planet. And you know, sometimes I find that it's confusing for students because it's actually a confusing process, right? If you think about the complexity of climate, you have atmospheric factors, you have earth patterns or earth rotational patterns, and then you have solar radiation, and all of these things come together to influence climate. So it isn't a clear story when you're looking at historical changes in climate. You know, you could have an albedo effect changing things. You could have a volcano, which could block out the sunlight and cause changes in the climate. And so one of the things that that is really clear, though, that we understand really quite well is this relationship between carbon dioxide and temperature. And it's very clear that high carbon dioxide equates with a high temperature. And one of the concerns we're having right now is we're just seeing the carbon dioxide climb higher and higher and higher. And we are seeing a correlated temperature changes in warming temperatures perfectly with that carbon dioxide. And so this is one of the biggest reasons that scientists believe that we are currently experiencing climate change. And now, as you'll find out in the subsequent lectures, we're seeing actually the models that are forecasting what these climate changes are expected to look like are becoming more and more true on kind of our real-time scale. Okay, so here again, you can see this relationship between carbon dioxide and temperature overlaid on a graph. You're gonna make a figure quite similar to this in the climate change lab. And again, looking, you cast back and you can see these temperature and carbon dioxide correlation. And if you notice, we have this huge spike here. And not very long ago, there was an article published saying that we are now have the highest carbon dioxide in the atmosphere recorded since humans have been on the planet. And there's a certain reality that we don't have a clear-cut answer of what's going to happen. It's clear that temperature is going up, but we don't know all the intricate details of how this is going to play out we have some pretty good models, and we're going to look at those models so you can really see what's likely to happen, and therefore we could potentially make some decisions about the best mitigation possibilities going forward. All right, that's it for climate, and we'll move to climate change.